Okay. So, hi everyone.
And I might just before we get going there, wondered if I think on my screen, I'm hoping that we can record. What, for folks that are joining us here, what are you able to see? Are you all able to see Dan's screen?
I'm able to see the screen there, John. Yeah, that the
Okay,
PowerPoint presentation.
Yep,
okay.
I second that.
Okay, thank you. I'm not sure. We'll see how this goes. I tried to do a recording of this. I'm hoping we capture that. But in any event, would like to welcome all of you to Dan Hamalaine's presentation this evening. Dan is at the conclusion of his capstone course, DIGA694, that many of you will be moving into in subsequent terms here before too long. And Dan focused a lot of his research for his capstone in a context of looking at machine learning. So there's different levels of machine learning. Some of them would get into imagery, some of them would get into other data sets and things like that at various levels. I know some here. Check this out here. Yes. Let's see here. Anybody else hear that? Okay, that was maybe Meg. So in any event, again, folks, if you check your mics there, and Dan will try to monitor that as well. But as we were saying, Dan's focus of his capstone dealt with machine learning, in particular, how trajectory prediction of autonomous vehicles, autonomous driving vehicles, and some of the AI kind of behind that, artificial intelligence and whatnot. And so Dan's study was looking at how data sets, kind of relevant to many courses, how data sets can impact different results and how that data is structured and missing components of that data as well. So Dan, we'll turn it over to you and let you share a little bit about, or a lot about your story here with the validation of machine learning based approach with predictive models and improved data. So Dan.
Thank you, John. So yeah, that kind of gets at the gist of what my capstone covers. So we know automated vehicles are, coming around the corner or whatever. At what point they'll all be autonomous on the road, we don't really know, but there are plenty of improvements, at least that they've been purported, mainly around improving traffic safety and efficiency. And this sort of makes sense. If we remove the driver from the equation, we can remove the human error that, texting and driving, drunk driving, any sort of thing like that. So there's a lot of potential there. But we know for sure that if all vehicles on the road are autonomous, they can coordinate with each other if, the business is allowed to do so, or if the government requires them to do so. So in theory, if the entirety of the road is just autonomous vehicles, we don't have to worry about traffic jams or anything like that, at least in theory, because they can all coordinate. But in the short run, autonomous vehicles will need to learn how to drive with conventionally driven vehicles, so driven by a human. In order for them to do that safely and efficiently, they would have to have a pretty good understanding of human driving behavior. And we might not realize it, but we sort of do this already as humans. We sort of predict where a vehicle near us is going to go just because, well, they're moving straight or they turn on their blinker. So we know they're going to go left or right. So we can adjust our driving around these sort of cues, whether they be very conscious or even subconscious. We sort of are able to navigate around the traffic context. But a computer could maybe do this a whole lot better, given the fact that they could explicitly look for certain behaviors and explicitly learn how to best operate as efficiently and safely as possible. So if a vehicle is provided the local history of its nearby vehicles, an EV could probably predict any likely danger and much more. It could maybe predict a way to avoid a traffic jam, avoid traffic jams from being caused, things like that. And there have been plenty of studies surrounding this sort of concept. And for my ends, I used one by the University of California, San Diego researchers, Nachaka Deo and Trivedi, their 2018 neural network model for trajectory prediction. So I'm going to present this kind of simply. So if a vehicle is given the last 3 seconds, if let's just say a computer is given the last 3 seconds of positions for vehicles on a road, mainly we're going to focus on freeways here. The last 3 seconds of the X coordinate, the Y coordinate, the time for each of those, along with any maneuvers that have occurred. And we specify these maneuvers as being a lane maneuver, that would just be changing lanes, or a braking maneuver, that would be slowing down or maintaining normal speed, anything that's not braking. Given all this, can we predict the future path of any given vehicle on the road? So given these 3 seconds of inputs, can we predict the next 5 seconds of all those things, predicting the XY position, along with any lane changing maneuvers or braking maneuvers, given this traffic context? So the original research that I'm basing my project on, they used the Federal Highway Administration's next generation simulation data set, which is originally, it comes from 4 different locations at numerous different times, but the idea is it's a massive amount of vehicle position data all together for a specified amount of time. And the 2 freeways that they used were Oakland's Interstate 80 and Los Angeles's US Highway 101, which are the schematics for which are featured on the right, and each during a period of rush hour traffic for one day. So each is from 2005. The Oakland data set comes from an hour in the afternoon. The Los Angeles data set comes from an hour in the morning. And it occurs during the time at which traffic progressively builds up to rush hour. So when traffic flow starts to break down and slow down. And in total, the data set from these 2 locations has about like 8.5 million vehicle positions from about 11,500 vehicles. So that's the kind of size of data we're talking here. And this amount is necessary for any, adept prediction model to be successful. You'll need massive amounts of data to actually teach it how to properly predict. But this is one of the only data sets available for the longest time, at least open to the public. And I'm sure there are plenty of data sets of smaller amounts, but none that feature just one single traffic context for one single period. And there are some issues with it. For one, Koifman and Lee in 2017, and this had also been found earlier, found that 13% of the vehicles from Interstate 80, they overtake the position of their leading vehicle, which basically amounts to a crash. And this is from one single day for one single hour. So 13% of the vehicles in this 1 hour span crashed, which seems pretty unlikely. Furthermore, if you look at the data, the vehicles don't behave as if they crash. They don't go off to the side of the road. They just sort of continue the behavior that had been exhibited prior. They also noted that an exceptional number of vehicles had really bizarre acceleration values, namely values that are over 3.05 meters per second squared. That is found to be abnormal by most research, along with some low constant speeds, which basically means they're going, let's just say at like a low speed, like 5 miles per hour for over 5 seconds, which is really bizarre, especially in a rush hour traffic scenario, to maintain a consistent speed for that long. And this sort of indicates that the positions themselves are probably error prone. But because it's the only massive data set available, researchers kind of have to turn to it for any sort of, advanced machine learning based model, because you need the massive amounts of data. But in 2018, a new data set like this came out from German researchers, and it's based off of 6 different freeway locations in Germany and spread across a total of 60 different subsets. So that's a lot more subsets, a lot more locations and whatnot. It also includes both directions of travel. So beforehand, these are the 2 highways from the NGSIM set. They're going in one direction, each having 6 lanes, including like an on-off ramp of various sorts. Whereas the high D data set features it from 60 different things from 6 different locations with both directions of travel. Only one of the locations features an on-ramp though, so the data is quite different because of that. And it totals to about 15,000, over almost 16,000 positions, 10 positions per second from 110,000 vehicles. So it's a similar size at the end of the day. So the scope of my project was to take this machine learning model, or this neural network model that predicts future trajectories of vehicles based on their past trajectory and the traffic context. And I wanted to see how it fares with a allegedly better data set. So to do all this, I wanted to first confirm the errors that other researchers had found in the NGSIM set, along with making sure there were no errors with the high-D data set, then pre-process that data for the model, and then confirm that the replicated model that I created, which is based off of the two researchers' GitHub repository, it more or less mimics exactly their code with a few adjustments. I just want to confirm that the results with the original data set are the same as theirs, because if they're vastly different, then it's like, okay, we're dealing with a different model here. And then to train and evaluate that model separately with the new data set. So from my research, I more or less confirmed what other researchers had found. From both of these locations, 10.5% of the vehicles overtake the position of their leader at one point, which is tantamount to a crash. Nearly all the vehicles feature the abnormally high acceleration, and 3.3% of vehicles feature the low constant velocities that I had been discussing earlier. And this more or less confirms that the NGSIM set is probably erroneous in its positions. Whereas with the high-D data set, there were none of these issues with vehicles overtaking their leader. There were no crashes, or no abnormally high acceleration, or no low constant steady speeds. However, in one of the data sets, in 3 of the subsets actually, vehicles ended up going in the wrong direction for a certain stretch of the trajectory. And these come from the only 3 sets where there's stop and go traffic. So it's likely that the tracking algorithm that they use wasn't able to fully process. It might have gotten used to seeing traffic flowing, not stopping and going. And then once it faced the stop and go traffic, it made inferences that weren't correct. But luckily, because there's so many subsets, we can just omit those 3 that had the erroneous vehicle trajectories. Another issue, however, though, is that vehicles begin their trajectory at various positions on the road. So suppose most of the vehicles, they start at the 0th X coordinate. Some start at the 100th X coordinate, which is obviously not reality. They weren't just plopped down onto the road. The tracking algorithm simply wasn't able to track them until they got far enough down the road. So this is an issue mainly because some of the vehicles will have missing neighbors, more or less, in that where a vehicle should have been in the lane to their right, it actually isn't because the tracking algorithm couldn't record it. So that's an issue because we won't have the full traffic context for our model to make its best possible prediction. So the solution that I implemented for this was to create a standardized cutoff, because most of the vehicles start around the same position. So let's just say the normal study area is from 0 to 500. I'm going to say it starts at the X position of 10, right? And anything beyond that, anything that starts before that is not going to be part of the model, or won't be fed to the model. But some of the vehicles featured very extraneous start positions, like well into the study area. So for these, because there weren't that many of them, I created a linear model that is able to predict how long it took them to get from the actual cutoff position to their fake starting position, using the velocity that the vehicle is exhibiting at their first recorded position. So it's more or less, you give it, hey, how fast were you going at your fake start position? Okay, this is how long it probably took you to get from the actual start position to this fake position. So now we know the number, now we know how long it took for the vehicle to travel from the cutoff to the fake start position, and therefore we can filter out the positions of any of their neighbors, because those positions don't have their full traffic context. And now that we know the times at which they occurred, we can actually filter them out and not feed them to the model. And this prediction model gives you the amount of time it took from the vehicle to get from the start, from its, the actual start position to its fake start position based on the vehicle's velocity at that fake start position. This model is created by using the amount of time it took for all the other vehicles to get from the cutoff to that position, whatever it may be, and the relation between their velocity at that position and how long it actually took them to get to that position. And then the positions of the vehicles that would have been neighbors with the vehicle missing its positions are filtered out and not fed to the model. So then once we've worked around those errors, we then simply need to do the pre-processing, so get the model its necessary variables. And in the original form, the data comes with X and Y coordinates along with the time of its position there and its lane. What the model requires, though, is these along with the lane change maneuver, the braking maneuver, and the neighboring vehicles. So we just need the IDs of the neighboring vehicles and their relative location to the vehicle in question. And this is done by creating a neighbor grid, which I'll show you later. So for creating these maneuver encodings, so whether it be the lane change or braking maneuver, we more or less encode a certain number 1, 2, or 3, or 1 or 2 to represent some sort of maneuver. And these maneuvers are based on the lane 4 seconds prior and the lane 4 seconds after the given the position in question. So let's just say we have an entry and they're at this certain location, and 4 seconds before they were at lane 1, and then 4 seconds after the position in question, they're at lane 2. So then we would encode this with the proper encoding to indicate that a lane change in a certain direction occurred. If no lane change occurred, we simply leave it at 1. And then we do the same for changes in velocity. So we look at the velocity 3 seconds prior to the entry in question, along with the velocity 5 seconds after. And we look at the ratio between these two. And if this velocity ratio is greater than 0, so that would mean that it actually is decreasing, and is less than 0.8, then we would encode it as we would say the vehicle is braking. Otherwise, we don't say it's braking. We say it's doing nothing. No braking maneuver. And then finally, we create the neighbor grid. And the vehicle in the grid slot in the center is the vehicle in question. And then at any given time in their trajectory, we have this grid where it shows the, shows the relative positions of vehicles nearby, and they're represented by their vehicle identification number. So we care only about the lanes adjacent, so the lane to the left and the lane to the right, and then the lane in which the vehicle is in at that entry. And then we only care about vehicles that are 27.42 meters in front or 27.42 meters behind. And that's equivalent to exactly 90 feet. The original study did this in feet, and I changed it to meters, hence these decimals. So each position in the grid is filled if there's a vehicle actually there. And this sort of gives us immediate access to the traffic context for the vehicle in question. So instead of having to look at, which vehicles are actually near us, we can just look at this grid, look up the vehicle's trajectory by using I used a hash map sort of key ID lookup to then get access to their trajectory, so then we can get the last 3 seconds of their vehicle path. The high-D data set is a little bit different though. Whereas the NGSIM set had the vehicle positions had the vehicle positions coming from the center of the vehicle. The high-D data set had the vehicle positions coming from the upper left corner of the vehicle's bounding box, which basically is how they track the vehicle. So I moved that to the center just because there were issues with lane changes. If the vehicle at all swayed to the left or right, it might accidentally trigger a lane change. So it would say it was in a lane for like less than a second, then switch back to its original lane. And that's due to the fact that the position is marked at the outside of the vehicle rather than the center. And then because the high-D data set features trajectories traveling both directions of travel, so it includes both east and west as opposed to just east, or north and south as opposed to just north. I flipped one of the directions of travel so it's consistent for the sake of the model, right? So if the model is presented with increasing X positions and then decreasing X positions, it might get kind of confused. It might be like, I don't know how to deal with these decreasing positions. So by flipping it all around, it's able to all be in the same direction. So the model doesn't have any trouble learning the tendencies of the roadways traffic. So then this brings us to actually training the model and getting it to predict well. And typically this is broken down into 3 steps or 3 different phases. The bulk of which is the training phase. And that is where we give the model a sample and then we tell it to predict whatever we want it to predict, right? And at first it's going to be awful at this because it just has unweighted, uncalibrated weights within the model, however complicated we made the model be, and it's going to be pretty bad at it. Then we give it the answer and it measures the error, like how far off are we from the actual trajectory with our prediction. And from there, the model can calibrate its weights based on how poorly or well it, predicted the trajectory. So as trajectories begin, if they make a certain change to the model that really improves the prediction, they're going to be like, oh, we should keep doing something like this, right? We should keep we should keep changing the model because this had a positive feedback result. So it keeps doing this with a certain amount of the data. And then after that, after one of these cycles is complete, the model is presented with a new set of data. And we present it with a new set of data because we don't want to look at a set of data that's already looked at. It already has the correct answers or has exposure to it in one way or another. So we give it a new set for it to operate with. And then the engineers creating the model can look, okay, how well did it actually behave? And now we can actually go and make changes ourselves to the general structure of the model. Was this a good change or not? They can learn things like that. And training and validation phases can continue inordinately. You can keep doing this over and over until you feel like, yes, this validation cycle had a really low error result. It's ready to be evaluated with a final evaluation set. And this can be thought of as like the real rubber meets the road moment where, hey, actually, how well will this behave with a completely new data set? Can we set this off into the wild and let it can we actually let autonomous vehicles use this? That's sort of what the evaluation set would be measuring is the final accuracy. And like I said before, these are split up into different data sets because giving the model exposure to them would be sort of like, seeing the answers to a test. And for this project, I did not do a validation phase of the cycle because my focus was not on changing the model itself, but rather changing the practices the data management surrounding it. So making sure that the data sets given to it are actually in its proper form and don't have issues. So this means we need to break apart these data sets into their proper partitioned sets. So the model or the research that I'm basing my project on, they had 80% of the vehicle trajectories in the training set, 20% in the evaluation set. In reality, they actually did 70% in the training, 10% in a validation, and then 20% in the final evaluation. But I just combined the training and validation because we don't need to do a validation. With a limited number of subsets, though, like there were with the NGSIM set, the way that they partitioned the data was simply by time. So vehicles in the first 80% of the data went into the training set. Vehicles in the last 20% time-wise went into the evaluation set. And there really isn't a better way to do this when you're trying to partition a single subset of data. You kind of have to do something like this. And with the limited number of subsets in the original data set, it's there's no way around doing it like this. And this has the problem of some of the vehicles in the partitioning split will end up being split off from their neighbors. So we again have this issue of vehicles are missing their neighboring context. The model is going to have, some bad information more or less. And it also has the issue of biasing the training set and the evaluation set towards different, traffic scenarios. So if I'm using the first 80% of traffic, well, that might be different than the last 20% of traffic, which might skew the results one way or another. So it's sort of biasing towards certain certain scenarios is the best way to think of it. So because the ID data set had 60 subsets, partitioning was a lot easier. We could just take a subset, put it in the training or evaluation set, take another set, do the same thing. There's much more room for a proper partition. And so how I ended up doing this was I created all possible partitions and then looked at the macroscopic traffic properties with the following constraints. So I needed to make sure that at a 4:1 size ratio, 80-20 split, I wanted to make sure that both the training and evaluation data sets had exposure to each location at least once and in each direction of travel. And I wanted to, at the end of the day, them to all have similar for them to both have similar macroscopic traffic properties. And this amounts to traffic flow, which is just how many vehicles came through in a certain amount of time. So how, if there's a lot of vehicles coming through in a certain amount of time, that is different than very few vehicles, or very few vehicles, but due to the fact that it's congested. So by making sure that the averages were as close as possible, we could somewhat be ensured that we weren't biasing one set towards certain scenarios over the other. So the final results, at first I'm going to show you the comparison with the original study that I'm basing my project on. And the results are similar enough. They behave well at some time steps, with each of these times being like how far out into the prediction horizon it is. So time 1 would be 1 second into predicting, time 2 would be 2 seconds in, and so forth. And as you go, further into the prediction horizon, the prediction error gets larger. And this error is measured by the distance between the actual trajectory positions and the predicted positions. So it's just like taking your distance formula and then taking the average distance of the predictions versus the actual trajectories. And that's what these numbers measure out to. So as you go further along, they get worse, which makes sense, right? I know that this vehicle's at this position. I know its last 3 seconds of travel. Okay, I'm going to be pretty good at predicting the next second, at least a lot better than predicting the 5th second, right? Because it's closer to what I know. And then this is to show the comparison with the 2 different data sets and in a similar fashion. And as you can see, the ID data set performs much, much better for most of the time steps in the prediction horizon. Once you get to time step 5, though, it does much worse than the NGSIM data set did. But everything else, it does just as well, if not better. So this goes to show that the ID data set is probably more reliable. It could, infer more from it, probably because it wasn't dealing with erroneous erroneous vehicle positions, and whatnot. And then if we take a look at the accuracy here of its ability to predict maneuvers, it's able to predict lane changes just as well, but it's able to predict braking much better. And that is indicative of the erroneousness of the NGSIM data set, right? If vehicles positions are randomly stopping and doing things that aren't in correspondence with reality and have no pattern or rhyme or reason, then predicting if it brakes or accelerates is going to be a lot harder than if it were actually following some sort of pattern that we could predict from. But as for the jump in error for the ID data set, if we take a closer look, the top left graph shows the comparison of errors. The NGSIM error, it's increasing, but it's sort of increasing in a linear way, right? It does sort of curve a little bit, but it's mostly following a linear path. Whereas the ID data set, it is, its error is below that of the NGSIM set, but then all of a sudden, or after 4 seconds into predicting, it jumps. It makes this curve. So it doesn't follow this linear projection. And if we look at the actual change in error across the time steps, this is even seen further. We can actually see where this change in error really starts to jump, and it's between 3 and 4 seconds. So for whatever reason, once the prediction horizon gets out far enough, when it's using the ID data set, it has issues with it. And one possible explanation might be the difference in velocities between the 2 data sets. Because the NGSIM data set is mainly focused, it mainly comes from rush hour traffic scenarios, the distribution of speeds is far less than that of the ID data set because it's mostly in rush hour traffic. They're going relatively slow. And we can see most of the vehicles are found in this box on the left. at or below 10 meters per second, which is not very fast at all. I believe that corresponds to about, I want to say somewhere around 20 miles per hour or so. So it's not exactly very fast. Furthermore, within the interquartile ranges, 0 meters per second is within the interquartile ranges. So a lot of vehicles aren't even moving for good parts of their trajectories. Whereas with the high D data set, it's much more spread out. We're dealing with much greater diversity of speeds, which means if the model is presented with one of these outlying speeds, it might have a lot more difficulty predicting that trajectory because it hasn't seen as many of those speeds, right? It's, oh, I'm not used to this sort of thing. I don't know what to expect. Is sort of the idea. But we would probably expect more of a linear relationship between the prediction horizon and the error, right? So as we see with the NGSIM data set, like I said before, it's sort of a linear relationship. The further out you get, the worse it gets. And it gets worse and worse consistently. Whereas for some reason with the high D data set, it jumps, which the distribution of speeds doesn't necessarily explain that. You'd expect more of a linear relationship with a greater distribution of speeds. So you may expect this change to be linear, like with the NGSIM set, but you might expect it to be, have a greater slope, right? It might start lower, but the slope might be higher, is what you maybe expect with a greater distribution of speeds, not all this kink in the graph as we see here. So the bottom line on all this, though, is that there's a limited number of data sets for us to use to calibrate these models, which presents difficulty for the autonomous vehicle industry because the only real way for them to get exposure to being able to predict and to being able to behave safely is actually testing on the road. Without these data sets, the only way they're actually going to learn how to best operate is by driving on the road, which seems somewhat dangerous, especially given the fact that there are, will be on the road at those times. So one way to circumvent this would be to have more abundant, more accurate trajectory data available to researchers or to industry leaders to implement better trajectory prediction, to best, to really hone in on the abilities for autonomous vehicles to behave safely. So I'll open up for any questions now, any comments, anything like that from anyone, if anyone has any. All right.
Thank you, Dan. Don't worry, we'll have a number of questions for you here as we, as we go here. Yeah, I'm going to see what we can do here for kind of a bigger group here of people. So if you have any questions, feel free to unmute yourself. See a few people maybe getting ready to ask you a couple of questions here, Dan. But Dan, first and foremost, just some general comments on a little bit of kind of the reflective overall process from where you were to where you are now. You did a ton of background literature research into this topic for quite a long time. So I remember back from where you were long ago to where you are now.
Yeah,
that was a big gap that you jumped, and especially having to go in there and learn different aspects of really kind of the behind the scenes, the data science, the kind of some of the deeper things that were involved in your project here. But a couple of general questions. One that you addressed, I had a question on the travel, the directionality, the flipping, which was interesting on that here too. One just kind of general process. Can you share maybe with people or in our group here tonight or whatnot about the general process that you went through when you were examining the data to begin with? Like what were some strategies that you used? I mean, evidently literature, but what were some other things that helped you study the data, learn the data?
Yeah, so because the data set, the high D data set was relatively new, there wasn't actually a ton of literature out there on it, at least when I started this, or when I first had learned about the high D data set, which was probably back in April of last year. There were only a handful of studies out there even about it. There's one that looked at looked at some of the errors that were found in it. And that sort of was my that's where I started. I used that, and then I looked for those errors, and then I learned, oh, it's actually due to these things. Got it. So it was kind of cool to have a novel data set to really actually examine and have to deal with. And there's a lot to deal with. I feel like I learned quite a bit about data processing and whatnot simply by having to examine and find any inconsistencies. The method I used mainly, this is all in the form of a CSV, right? So I wrote up a few Python scripts that would sort of look and comb through for any anomaly. So I'd look at a given vehicle's trajectory, and then I would look for, okay, is it behaving the way I expect? So at first, there's going to be plenty of anomalies because I don't know what to expect. And then as I go through and I examine more and more, I'm like, okay, now I actually know what I'm expecting. So I can write some sort of script that can look for these sorts of things. And as frustrating as it was, it's pretty rewarding just to sort of realize, oh, I actually figured out why this is behaving this way, or oh, this issue is contained to this date, this subset, or this is contained only to vehicles traveling in one direction. So, for example, with flipping the direction of travel, for the sake of the model, that's, like I said, inconsistent direction means, oh, the model is going to sort of be flustered when it's presented with, different directions of travel. So trying to come up with a solution to that, was a matter of just sort of, honestly, it was a matter of like, all right, I'm going to write something up in Python. What's the outcome? Oh, shoot, it didn't really get what I wanted. And then look at the CSV and see if it got what I wanted. For that specific one, the solution ended up being, I take let's just say the data runs from 0 to 500, right? So it's a 500 meter long study area or something like that, with each X position being numbered off, 0 to 500. For vehicles traveling from one direction to the other, they might go from 0 to 500. The other direction will go from 500 to 0. So to reorient that, I want the vehicles in that backwards, so to speak, direction. I want them to start at 0 and end at 500, as opposed to starting at 500 and ending at 0. So the way to fix that, at least in the X direction, would just be you take each position, you subtract 500 from it, and then you take the absolute value of that. So the position of 500, that would turn into 0. The position of 100, that would turn into 400, and so on until the position of 0 turns into 500. So, and then they have to do the same thing for the Y direction, just because that's also flipped. So that's sort of one of the workarounds. And there are plenty of workarounds that I didn't mention that you have to do. So as I was doing all this, I was thinking of all of the data, data management practices that were taught. And I was like, oh, thank God, it helps to even be aware of it, because there's plenty you need to do, especially with such a new data set and something that doesn't have very much standardization to it at all. You really need to figure out a way to standardize it for yourself. So
I appreciate sharing that. The so much of what we do with capstones or projects, things like that, data is in all different types. So for many people that are embarking on this journey, some data is a little bit more clean, if you will, than it is of others. And I guess where I was hoping that you would highlight, and you did, is that there's a lot of time that needs to be invested into data when you need to try your best to build a design that adequately compares them, if that's what it is you're trying to do. It's not the glamour sometimes. It feels like a marathon, when you're combing that data, trying to build it. And you mentioned a couple of really good key points there, from standardization to figuring out what you need and just exploring the data and examining fields. And there's quite a litany of things that I know that you did go through. Not every project needs to have Python scripting involved in it. It's just something that you had to do some of that to make your work a little bit easier. So I appreciate you sharing on that. Dan, one thing I was hoping that, and you, I guess, kind of talked about a little bit there, but after going through the journey that you did, some models are designed based on data maybe as good as what it was at that time.
Mm-hmm.
We're living in an era where 10, 12, 15 years ago, we thought, boy, I have a cool set of data. That data might be good for a year or 2 or 3. Back then, now that data's ready to be replaced next year sometimes. And so looking back at what it was that you did in comparing these two data sets that spanned a few years, seeing some of the potential, I guess, issues, maybe, no data set's perfect. What do you think or believe could benefit the next iteration of data the most to improve the results?
Any sort of validation of the tracking software, right? So John had mentioned at the beginning in the introduction that a lot of machine learning models do image processing, and that's what these utilize to actually track the vehicle position. So how they got it was they were in the older data set, they recorded from buildings adjacent to the study sites that were tall enough and used multiple cameras and sort of synchronized them up. And then from those cameras, they used tracking algorithm softwares that they had contracted out to detect the trajectories. And that was at the time when this was like in its infancy, brand new. And just given that sort of scope of what they're trying to go after, it actually in hindsight seems crazy. Like they were going after this thing with barely any experience, and it was kind of amazing that they're able to do it. The Federal Highway Administration was able to do it. But clearly it had issues. And when you have multiple cameras, that's going to have some issues because you have to like translate from the transition from one camera to the next. So it has those sorts of problems. Whereas with the newer data set, the ID one, they just used a drone flying directly overhead. So that vantage is it's much more advantageous for this sort of thing, especially when you're able to use a single camera. So I would say one way to improve it would just be, hey, let's actually like, before we release any data set, let's go and take a vehicle. We'll maybe put some sort of like, I forget what you call these things, but some sort of black box is able to actually, a GPS tracker that actually tracks our position of the vehicle that we're driving, and we know where we are. And then we're going to compare it to the results of the, tracking algorithm that we used. So doing that and iterating that multiple times. I'm sure they did that to a certain extent, but really getting that down and focusing on getting a really accurate data set, because even with the ID one, I'm thinking like, I don't know how accurate this is. They purport that it was within 10 centimeter positional accuracy, but given the fact that some of the vehicles were traveling backwards when they should have been traveling forward, that's probably not true. So it would be great if they were able to really validate that these tracking algorithms worked. That would be super helpful for having, an accurate data set. And even with things like fields, like I was at one point considering like, does it matter the Y position? Maybe I just need lane, because from the perspective of like an autonomous vehicle, they don't necessarily care where within the lane you are. They care which lane you're in and which lane you're going to go into. Now, obviously, you moving within the lane might be indicative of a lane change, so that is important. But at the end of the day, what this model would need to predict is ultimately where are they going to be in terms of the, where in the traffic flow are they going to be and which lane are they going to be in. We don't necessarily care if they're at a certain position within the lane when it comes to the prediction. So anything that would make the data more accurate and anything that would be able to somehow like fine tune what is necessary, so then you don't have to track as much. So if you're able to just track the lane, it might make it easier for these tracking algorithms to actually operate as effectively as possible.
Spatial error is a huge component of what we're doing in anything. When we're assessing our results, it's what is the spatial accuracy. Not every project's going to have spatial accuracy, but that could certainly benefit yours. Even when we're talking about lane changes and predictive modeling and whatnot. Let's see, other questions for Dan. Jerry, I think was a question there. Go ahead, Jerry.
So not so much about the data itself, but as far as the project, what was, as far as you yourself, Dan, as a student, what led you to decide this project?
I have a weird obsession with like vehicle traffic. Like any sort of, it might have stemmed from just like maps and looking at roadways and whatnot, but I have a weird obsession with like, man, are we really bad at driving? Because when you're driving, everyone around you is the worst driver ever, but you're not. You're great. You're a great driver, right? Like, no, you probably are just as bad as everyone else. So it's that sort of like, man, what would be the optimal driving tactic? How would it be best to actually drive? Like, people are always complaining about merges, like zipper merge and stuff like that. And I'm thinking in my head, like, what would be best for any given situation? And there's no way to know that unless you have a vast amount of data and a clear and concise way of breaking it down. So that's what led me to this, really, was I was interested at first in traffic models. So things that take in like, oh, this is how a vehicle behaves. We can model it out based upon like the distance to the vehicle in front of them, all these sorts of things. And I was like, okay, how well do we know that these models behave? There's no real way to know how accurate the model is unless we have actual data. So then that led me to the different data sets, and I became more interested in those. And then eventually it led me, I found one study that, the study that I essentially had replicated. I found that, and I found it really interesting. And I found a lot of other ones that were based on that, ones previous to it. It just seemed like a really interesting application of it all, because for an autonomous vehicle to behave as best as possible, they really have to figure this sort of stuff out, unless they're only dealing with other autonomous vehicles. But that, we don't even know if that'll ever happen. Can we envision the government banning, conventional, like human-based drivers on a given road? Maybe I could see it, but maybe not. So that seemed fascinating to me. And the fact that there was this literature out there was both surprising, and then I realized I shouldn't be surprised. Of course it's out there. It's pretty important. So yeah, that sort of obsession led me here.
Thank you, Dan and Jerry. Other questions, comments for Dan?
I have a question.
Jim, yes.
That was a really, really impressive presentation, and
Thanks.
really interesting. Some of it went over my head, but one of the last couple slides that you had of those graphs,
Sure,
like the NGSIM data, showed that there really was not much of a change in the amount of error that took place over the time.
yeah.
Right there. Whereas at about 4 seconds, there was a abrupt increase in the percentage of error that took place. And trying to figure out what could be the explanation for that, you suggested that there was a difference in the velocity between the high D group and the NGSIM group.
Yeah.
I wonder if it'd be feasible to subset the NGSIM data to take a subpopulation where the velocity approximated the velocity of the high D group. And if the fact that the curve is so flat makes me think that probably it wouldn't really explain it, but that would be a way of exploring whether or not the velocity of the vehicles explains why the error abruptly increases at 4 seconds. Can you even do that with this data set? Can you even select out a subpopulation like that? Yeah,
you totally could. You could, the way I was thinking about doing something like this, and that's exactly kind of the question that, that's how you would figure that out, I feel like, at least I personally believe. And how I would go about it is, instead of feeding it just a certain set of data, I would try to almost give it equivalent to like a cookie, right? Like on your computer, on the internet, like this sort of thing. All right, when it makes a prediction, all right, it made a prediction for this kind of trajectory. All right, what type of trajectory does this count as? Let's count the error, and then also count that, hey, this is a trajectory that was traveling over a certain velocity. We're going to mark that so we know, hey, this is due to this sort of, like, this error came from this type of trajectory. And you can break that down numerous different ways, right? It could be based on velocity, it also be based on like whether the lane change did occur or not. One of the things that this sort of reminds me of is that these maneuver accuracies are probably misleading, because most of the vehicles probably aren't changing lanes. So your best strategy may be just to say none of them change lanes, unless it's really obvious. So like these kind of accuracy measures are a little bit they're not, it doesn't fully explain. What you'd want to know instead is, how many did it get right? When it made a prediction for a lane change to the left, how accurate was it in that situation? As opposed to just a general accuracy sort of claim. But yeah, if we were able to somehow like, hey, these errors, we could break down like where the errors came from, right? Or like in some sort of way, simply by just marking them in a CSV or something when we're given the different error values when we're evaluating. That'd be one way to go about it. So yeah, there would be for sure a way to do that. And I wanted to do it. Figured was running out of time kind of thing though. I kept adding more and more, and I was kind of like, I can't do that. So, but no, that's a great idea.
Thank you.
Yeah.
Always easy to add at this stage that I was doing. But any other questions for Dan, comments? I think to Jerry's point, if anyone has any other questions there, for many of you in the journey of thinking about Capstone or the potential ideas for that, largely these are all scalable, you know, and Dan mentioned you've just had a passion or an interest in that. And so many of you are going to find a journey that speaks to you, things that you like, you know, things that aren't maybe quite as favorable for you, you know, select something that you generally like and look kind of behind the scenes to see what you might pursue. So there's a lot of ideas, a lot of possibilities out there. So just wanted to throw that out there, that there's a ton of variety, and pick something that you enjoy. That's a passion of yours.
Yeah.
Any last questions or anything like that for Dan? Okay, Dan, on behalf of the program, the Department of Resource Analysis there, we'd like to congratulate you on your conclusion of your academic requirements. So we thank you for all the years of friendship and community, and we ask that you, Pear is clapping there for you, so that's great. Don't worry, we're going to give Dan a round of applause here in a minute. And, but I do want you to go forward and share many of the great adventures in life with us and our community, and we look forward to adding you into the alumni pool here of well-respected alumni that are out there doing great things. So on behalf of us all, Dan, thank you very much. So I'll probably clap, and I don't know if anybody else can clap with me there, but I know I'm also clapping for quite a number of us, staff, faculty who weren't unable to join us here tonight, and appreciate everybody giving Dan a round of applause for that. It's always kind of funny virtually to do that, but Dan, the sentiment is all true and all real from us to you. So thank you very much.
Appreciated.
Yeah, thank you, Dan. And so with that, we'll go ahead and stop our recording here and do some wrap-up items, and then begin with phase 2.